Welcome back to this second session on testing and security at ESEM 2021. In this session, we will have also a mix of three technical papers and two papers from the emerging results and vision track. We start with the first paper, Barriers to Shift Left Security, the unique pain points of writing automated tests involving security controls by Danielle, Gonzalez, and others. I'm going to bring Danielle up on stage. Okay, Danielle, I think you're ready. Please.
Can everyone hear me?
Probably yes.
Okay, great. Thank you for joining me. My name is Danielle Gonzalez. This was a project I did during my PhD at RIT with a master's student, Paola, and my advisor, Mehdi. This was part of a larger study that we did exploring the practices, perspectives, and challenges of shifting security testing left into the unit and integration level. And the reason why that is important is that in modern development, lifecycle methodologies, whatever you'd like to call them, there's most often this sort of DevOps cycle where you're continuously coding, testing, building. And so now new methodologies for secure development have sort of added all these different activities for security into this. And that includes this very low level security testing at unit and integration levels. But this type of testing, this writing tests for security scenarios specifically, is a non-traditional application of what is to developers familiar infrastructure and practices. So they know how to write these tests already, but they're usually doing so for different types of functionality than their security controls, or at least they're not focusing on it from a security perspective. And the problem here is that there's little empirical evidence of potential barriers that would impede explicitly security-focused testing at this level. And when I say barriers, I mean more from the developer's perspective. So actually getting them to do this, which is its own problem besides having the right tools. But when developing those tools, understanding these pain points and how developers actually approach these problems, that must influence the development of these things, because there's already an observed gap from previous work between available security resources, such as documentation and examples, and the actual tasks that people struggle with. So to sort of address this lack of empirical evidence into this issue, we collected a data set of 525 Q&A posts about security unit and integration testing from Stack Overflow and in Security Stack Exchange. And we chose this approach because it allows us to understand these problems in the developer's own words. And these platforms are already heavily used by developers, so we're not trying to force them into a scenario they wouldn't normally be in. And we collected this data using an existing data set collected using PU Miner from MSR 20. And that data set allowed us to, it was already a set of security related posts. And from there, we just needed to filter to find ones that were related specifically to security testing at unit and integration levels. And so our main research questions were to understand what the key topics discussed in these posts were. So this is sort of a hint at what are they actually testing. And to do that, we ran LDA topic modeling on the text from all of the posts in the data set. And then the second question naturally was, what are the pain points that developers were asking for help with? And to investigate this question, we did manual data coding of 50 randomly selected Q&A posts. So from the 525 posts that we actually collected, the median score was about 1. So we chose this sampling to look at a collection of the top posts. We wanted to get all of the information about topics from the entire data set, but then we sort of paired this with this smaller sampling of manually coded data. And so this mixed method approach allows us to make inferences about both the broad community as well, early extent. So the first key finding were the topics. And so the discussion topics really reflected the subjects under test, which is what we expected, and some security scenarios. So by subjects under test, I mean things like the SSL certificates, protected resources, client and servers, and then security scenarios being things like authentication. And the key findings from our analysis of the pain points were that developers experience at least 7 when writing this type of test. And they occur across all of the test phases, so test planning, design, construction, maintenance, execution, but test design, so actually constructing fixtures and things like that, was the most impacted. They affected efforts to test at least 9 different security control scenarios and components, as shown by those topics. And one of the most prominent issues, this was actually something that happened across the different pain points, was that the complexity of third-party security APIs and frameworks and developers' difficulty using them specifically in test environments was a big issue, common theme amongst them. And we also noted that security controls can also make common unit test tasks or tests that don't implicitly have anything to do with security uniquely painful. And finally, even if security testing is not the goal, because they can involve security-related code, as I was just saying, they can still experience pain points outside of security testing context, which actually sort of elevates the importance of understanding these issues because it extends outside of security-specific testing. And so the first pain point that we observed was mocking security components. So this is the design and configuration of mocked fixtures for security components, such as authentication providers, as shown in the example here, things that use third-party frameworks. So most security controls, authentication, authorization, etc., are built using these frameworks. And this is a good practice because it absolves this developer the responsibility of having to figure out how to implement different types of authentication themselves. But this complexity has consequences because they also have trouble debugging these things. In this example, the poster was trying to test an OAuth authorization authentication using a mock MVC class, but they weren't able to figure out why a custom authentication provider they had created using that library was not working. The next pain point was interacting with security services and APIs. And so this is specifically not knowing how to test something. And the theme here was that this involved distributed or third-party security services and APIs. And people just did not understand mostly what components were supposed to be simulated and when they were actually supposed to be using real interactions, such as this example here. This person wanted to test an integration with PayPal, but they didn't understand what they needed to simulate. The third pain point that we observed was creating user fixtures. And this is because of the unique way that security controls actually interact with user data. So when developers were trying to test login and password validation scenarios, they didn't understand how to design appropriate fixtures. And when they incorrectly configured credentials, they had really confusing test failures that they didn't know how to fix. And so that's really what they were asking their peers for help with. So in the example here, this person has verified that their user fixture is correctly being loaded, but their login command is failing and they don't understand how to debug this. And they even note that they've read every single internet discussion pertaining to this. So they've tried several other places to look for solutions to this and they did not find them. Next, we had bypassing access controls for protected resources. So the procedure that people use for simulating authenticated states or skipping authentication entirely, it's very dependent on the system that's actually being tested and all the different tools and libraries that they're using to implement the security controls. So again, they had issues designing these tests and then debugging the errors and failures because they would miss or incorrectly implement one of the steps needed to do this. Such as in this example, this user's trying to integration test an OWIN test server, but they don't want to include authorization, so they want to know how they can fake authenticate and bypass a specific attribute. This kind of leads into the design of authentication flows. So because specifically for authentication, there's a lot of complexity and framework-specific properties of authentication flows. So for example, if you think of Spring Security, you can use it to implement multiple different types of authentication, and you can even have multiple types within the same application. So it's meant to be very highly customizable, but again, consequence is complexity here. So developers don't always understand the exact sequence of events that need to happen to recreate these low-level scenarios. And this is kind of also a reflection of confusion between doing this in the actual source code and doing so in a test environment when some things are mocked and others aren't. In the example here, the person wants to log in using form authentication, but they just don't know how to write the test for this. So this is sort of test planning and design. Next is creating HTTP request objects. And the first thing to point out is that this is not an activity that's specific to security unit testing. This is something that developers would need to do in a number of different types of tests, but it's uniquely painful in this context because errors caused by incorrectly configured login routes, trouble attaching certificates, tokens, and credentials to request objects caused a lot of frustration with failed requests and debugging. Specifically in tests involving security controllers and authentication. And again, as I mentioned, developers would say that they knew how to do this in production, but specifically not in their test environments. In the example here, this person is trying to test HTTP authentication. They've taken some code from blog posts that they found, trying to spoof headers, but it's just not working and they don't understand why. And finally, configuring systems for test environments. So understanding what settings, configurations, et cetera, to adjust and how to do so was a very painful process, especially with certificates and distributed components because of the issues with mocking in most cases. So in this case, this person was using Maven and it kept trying to use an expired certificate, and no matter what they did, it was still being found. And so these insights are important because they allow us to move forward in a data-driven manner. So we understand specific problems that could impede developers' willingness or ability to write these type of tests. And these are different ideas that we can take with this information and move forward. So things like automatic generation of text fixtures, interactive assistance, so a more teach a person to fish kind of approach, walking them through it, support for test planning, help developers identify test cases that involve security-related code. And then really creating more developer-centric guidelines and resources for this level of testing. So making sure that, different tools and libraries should have specific documentation for using these tools in test environments to maintain context. And we need a lot more actual code snippets and examples in documentation overall. So thank you very much.
Thank you very much, Danielle, for the talk. While the audience warm up, I have actually maybe curiosity on the last issue you mentioned of documentation.
Sure.
Do you have any insights from going through this data set that the developers, as a rationale, they point out to poor documentation? Or
Sure. So there was some prior work that I noted in the beginning that specifically looked at this issue and found that in our investigation of posts, our paper actually includes a smaller investigation into the different links that developers posted. I omitted it for time, but we did look at links and kind of map them to topics. And so in posts like where that person was saying they checked everything on the internet, they would put some links there and we looked at it, and some things would be included that we would think would help. So Spring Security actually has one of the more comprehensive test-specific sets of documentation, but even still, people were struggling with configuring their mocks. So it looks like what's really missing is sort of a troubleshooting FAQ in these types of things. Like here's how you set it up, but not a lot of information about, okay, well, if something goes wrong, here are some things that you can try. So that type of information.
Thank you. Okay, I don't see any question in the chat, but I also have a question regarding maybe one next possible step for this line of research. Do you think, how close are we to create a taxonomy of shift left security for testers? Is this a good first step?
When you say a taxonomy, do you mean a taxonomy of the pain points? Sorry, my sunlight is...
Well, yeah, I think the pain points are a first step into this. Or into having a comprehensive classification scheme where we can identify the different uh, things that belong to this security shift left.
Sure. So actually, this is it's the focus. It was the focus of my dissertation. So I've also done work creating sort of a taxonomy of actual test cases for authentication. And so I hope that others are inspired and continue to work. So far, it's not a huge area of study for the research community, but with this increased really adoption of DevOps, DevSecOps in practice, it's really important that we stay ahead of things and really understand these issues and problems as we're trying to build solutions for these type of development environments.
Okay, thanks. I'll make sure I'll check it out.
Yeah.
Okay. Thank you once more, Danielle.
Yeah, thank you very much.
Move on to the next speaker. And next, we have Pascal Gadient from the University of Bern, talking about security smells in mobile app servers. Let me bring Pascal on stage. Hello, Pascal. Stage
Hi,
is yours.
everyone.
Please go ahead.
Hi, everyone. I'm really excited to be part of ESEM 2021. I'm Pascal from the Software Composition Group at the University of Bern in Switzerland. I will talk for the next few minutes about security smells that pervade mobile app servers, and I really hope that I can not only raise awareness of the problems that we discover, but also provide you simple remediation strategies that would reduce the impact of most, if not all, of our reported security smells. This work was a collaboration between other members of our group, namely Marc-Andrea Tarnutzer, Oscar Nierstrasz, and the University of Auckland in New Zealand, namely Mohammad Ghafari. You may wonder why we show you a wedge of Swiss cheese. Well, cheese has many similarities with code. It usually smells and has lots of holes. A code smell is not necessarily bad, but it can indicate a potential vulnerability. Security holes or vulnerabilities, however, can be exploited by adversaries to steal customer data and represent a real threat. In previous work, we found that security code smells in Android apps are essentially everywhere, and many of them lead to actual vulnerabilities. For instance, we could detect the common task affinity smell in more than 99% of all apps that was caused by inappropriate default values. With this knowledge in mind, we asked ourselves one question: what about their application servers? To answer this rather simple question, we started to collect connection data of the URLs used in 431 open source apps from the F-Droid market and in 889 random closed source apps from Google's Play Store. From these apps, we could gather more than 9,700 URLs that we further exercised. That is, we sent an HTTP GET request for each URL, and we collected the returned HTTP header and body information. With this information, we were able to perform more detailed investigations. What you see here is a typical HTTP response header. The HTTP communication protocol uses header fields to set up a connection between a client and a server. These header fields consist of key value pairs that contain plain text. Moreover, arbitrary fields can be introduced by developers. In this work, we focus on specific response headers that relate to security. For example, the server and the x_by header field. Such fields leak the currently used software environment and offer adversaries a convenient way to search for potential exploits in publicly accessible vulnerability databases to compromise a server. You may think, is this a real problem? Let's have a closer look at the two highlighted entries that we collected from a server that has been mentioned in an app. As we can see, the HTTP and the PHP daemon are heavily outdated. They were, at the time of our investigations, almost 14 years old. As you can imagine, the well-known NIST vulnerability database reports plenty of vulnerabilities for these two services. There exist 74 reported vulnerabilities for this particular Apache web server, and there even exist 373 reported vulnerabilities for this particular PHP server. Now we are ready to look at our first research question. What is the prevalence of the server-side security smells in the web communication of mobile apps? In this work, we investigated the prevalence of 6 different security smells in servers that are referenced in Android apps. However, due to our limited time, we will only focus on 3 of them. In particular, we will look at disclosure of source code, disclosure of version information, and missing HTTP strict transport security, or short HSTS, which all can be resolved with rather simple techniques. To analyze the smell disclosure of source code, we constructed lightweight parsers for major programming languages which can detect occurrences of code leaks in error web pages. Because common frameworks offer facilities to publish detailed debugging information in case of errors, the corresponding HTTP bodies usually follow the same structure and are rather simple to detect. What you can see here is the number of affected URLs for 5 common web development environments, that is, ASP.NET, PHP, CherryPy, which is a minimalist Python web framework, Java, and Node.js. It is interesting to see that such leaks occur in every major language used for web development. However, they occur rather frequently in ASP.NET instances. In fact, 21% of all Microsoft IIS instances leaked source code, which indicates a flawed default configuration for some releases of this particular software product. To analyze the smell disclosure of version information, we relied on the HTTP header data returned from the servers. We can clearly see that version information in one form or another is attached to numerous responses. And the most common one, server, has been used in more than 2,400 URLs. In other words, that single header field appeared in the responses of about 26% of all tested URLs in our dataset. Again, we expect that improved default configurations could resolve this threat. As before, we used the returned HTTP header data to analyze the smell missing HSTS. HSTS is a security measure which ensures that a rendezvous with the server must start using an encrypted HTTPS communication channel. HSTS requires a max H value in the corresponding header field that specifies for how long this requirement remains active. Moreover, stable configurations can be added to a preload list, which is already embedded and continuously updated in popular HTTP clients. As a result, an adversary cannot downgrade encrypted communication to plaintext HTTP because the client already knows that all communication with a specific server must remain encrypted. Unfortunately, 86% of all URLs do not use this feature. And even worse, of those which support this feature, many use inappropriate max H values. Once the server administrator is confident that the implementation works, max H values of 2 years and an entry in the preload list are recommended. The mentioned findings clearly raise doubts regarding the maintenance of such servers. This sets the stage for our second research question. What is the relationship between security smells and app server maintenance? In order to assess the configuration changes, we accessed the same URLs twice within 14 months, a time period of which we expect that most servers would require some software maintenance. We collected the version numbers provided in the server header field and investigated whether and how the version number has changed. We can clearly see that the servers behind the majority of URLs that leak version information receive no updates. Moreover, it appears that such servers are rather short-lived, and almost every sixth server is shut down after roughly 1 year. When we compare the number of security smells with the server configuration changes, we can investigate the problem from another perspective. In this plot, the x-axis represents the number of security smells per URL, and the y-axis illustrates the number of affected URLs. On the one hand, the reduction of security due to service downgrades is quite rare among the tested URLs. Only 4 URLs were affected by such a downgrade. On the other hand, however, the overall security has merely increased because the servers behind most URLs do remain unchanged. In general, we can see that the servers of URLs suffering from 3 or more smells are usually not well maintained. We now get to the end of this presentation. As we have seen, app servers suffer from security smells and vulnerabilities. Fortunately, these issues can be resolved with rather simple methods, such as an improved default configuration and server maintenance, which eventually lead to improved app security. In more general terms, we can say that smells and holes plus simple methods lead to a superior outcome. And you can guess, this also applies to cheese. Swiss cheese with some heat and other basic ingredients transforms into the delicious Swiss fondue. If you haven't had a chance to try it, I highly recommend it. And this concludes my presentation. Thank you very much for your attention.
Thank you very much, Pascal. I have a question or curiosity related to, you mentioned that you took 2 measurements of this data 14 months apart. When was that? How recent is the data, basically?
So the first measurement was in 2017, and the second measurement was in 2018, like end of 2018, beginning of 2019.
Okay. And so do you expect that after now 2.5 years, the trend has improved, or are you actually planning to do another measurement?
So based on other studies on different aspects of HTTP communication, we can expect that the situation has improved. However, as we have found, it seems that app servers are more vulnerable to security issues than websites in general. Because application servers are usually just one-shot solutions. So you configure the servers, you set them up, and then you never touch that system again. And in our opinion, this is a severe problem that needs attention.
Yeah, it's actually also quite interesting to see that closed source apps were the most impacted by those smells. Do you have a maybe feeling for it?
So open source apps, like we use the apps from the F-Droid store. So those apps, like the source code, is accessible to everyone. And we expect that on the one hand, you have source code that many people can look at and just find bugs and resolve them. And on the other hand, like people that would actually use credentials and password protected content, they wouldn't add those credentials into the publicly accessible source code. So in my opinion, these are the 2 main reasons that improve the security for open source projects.
Right. Makes sense. Okay. Thank you, Pascal, for your talk. We can move to the next presenter for today. And this is going to be also a paper from the main track. Who are vulnerability reporters, a large-scale empirical study of free and libre open source software by Nikolaos. Alexopoulos. Let me bring Nikolaos on stage. Here you are, Nikolaos.
Yep.
Hello. We can see your slides.
Hello. Yeah, everything should work.
Yeah.
Okay. Yeah. Hello, everybody, and welcome to the presentation of our paper. I'm Nikolaos from TU Darmstadt, and my co-authors Andy from Reed, Dorian, Max, also from TU Darmstadt. And in this paper, we'll look into the question of who reports security vulnerabilities for big free software projects. So let's start with a quick overview of the structure of the presentation. So we'll go over some motivation, prior work, our goal and research questions, our dataset creation methodology, a few of our results, and a quick summary of the presentation. So starting, why even measure vulnerability reporters or characteristics of vulnerability reporters in FLOSS ecosystems? Well, the human aspect in the vulnerability discovery and mitigation process is often overlooked, but it's very important. It's very important because measuring characteristics of this human aspect can help us improve security metrics and can help improve community engagement, and overall can help us build a better understanding of the vulnerability discovery process. I have a little example here that shows how such measurements may in the future contribute a lot to improving security metrics. So imagine two projects, X and Y, that each have 100 vulnerabilities disclosed in a year. What does this tell us about the security of the projects? Well, since the last presenter talked about Swiss cheese, there was a blog post some years ago by Brian Krebs that said that all these companies that publish reports, like, I don't know, Windows has twice as many vulnerabilities and something else, are nonsense. And it's like trying to measure the quality of software. It's like trying to measure the quality of Swiss cheese by the number of holes you can find in it, which I guess is not accurate. Okay, so imagine, through some kind of magic way, we had a way to know how many people and of what skill level and for how long and so on were looking for those vulnerabilities that were discovered. And, this magic would lead us to a pretty good indicator of quality, meaning some indicator of the difficulty of finding a vulnerability. And such measurements like this one on the human aspect can help us, go towards something like that. Now, moving on, most prior work either focus on user studies, which are by nature small scale and focus on the tools and process used, or studies analyzing bug bounty platforms, which are confined within the platform, and their focus is to improve the productivity of the platform. Whereas our study is large scale, large coverage, meaning we want to cover as many of the vulnerabilities that we know of for the project that we choose. And we focus on indicators of effort, effects over time, and differences between projects. And our goal is to analyze historical vulnerability reporter data for mature and successful free software projects for two reasons. First, to identify common trends and practices that can be used as benchmarks of community engagement. And second, to identify potentially empirical metrics that could be used as indicators of software security quality. So our research questions are structured in two groups. First, regarding the distribution and temporal characteristics of vulnerability reports and reporters. So how are reports distributed among reporters? Do more CVEs over time mean more reporters? How specialized are reporters and for how long do they stay engaged? And the second block has to do with the motivations. And here we look into bug bounties, we look into affiliations, whether reports are internal or external to an organization behind the project. And if reporters also contribute via code commits or other bug reports. Okay, now moving on to the data set creation methodology, which is very, very important in this paper. So we start with selecting projects. We chose 4 big free software projects with a high number of CVEs and open process, meaning transparent logs of everything. And that's the Mozilla Suite, PHP, the interpreter, the Apache web server, and the Linux kernel. And of course, for vulnerabilities, we took the vulnerabilities from the MVD. That's the vulnerabilities that get a CVE identifier. Now, however, the tough part is to find the reporters. And so we used a wide range of sources, ranging from project-specific advisories to Debian security advisories, and other advisories that have information about all projects, to the backtracking systems of some of the projects. And we tried to get information who got credited with a discovery. So how did we do that? For some sources, it was simple. There's a field that says credited or something like that. And for other sources, we had to do a little bit of natural language processing. With regular expressions, we analyze a little bit the sources. So for example, this is a Debian security advisory. They use some keywords like discovered and reported. And we use regular expression to find these keywords and find possible reporters. Then we find other keywords like and. So there are 2 reporters there. Further keywords to extract affiliations like of or maybe parentheses, something like that. We also parse those. And the affiliations as well. And for example, from this security advisory, we got the following information. There's also other things that we do: extract email addresses, Twitter handles, again, regular expressions, remove noise, remove generic reporters, merge reporters, for example, same email. And finally, we went over all the data set all the reporters that we gathered for manual corrections and assigning a tag to organization. So the fruit of our labor is like a pretty big data set, more than 2,000 reporting entities tagged as either human or organizations for around 5,000 CVs with pretty good coverage for all projects. Now I'm going to try to give a quick overview of the results. First, regarding the concentration of reports, this is the same data in both plots. We see that only a few reporters have a large number of reports. So x-axis is just the reporters ordered by the number of reports, and y-axis number of reports. Most reporters have very few reports. We can see on the right here, for example, like here in the log plot, more than 1,000 reporters have only 1 report. Around 200 reporters have more than 10 reports. Yeah, so we see a power law-like distribution, heavy tail distribution. Reminds us of the Pareto law of for example, 80% of reports are made by 20% of reporters. And we see 2 groups of reporters. We can say like the dedicated ones and the many eyes of the community that are many, but have a few reports each. Yeah, and we can use a generalized Pareto principle. So, okay, the Pareto principle says the 80-20 law, but it's just for one specific exponent of the power law. Yeah, so some projects are more concentrated, some projects are less concentrated. We can read, for example, for Linux, 72% of reports come from 28% of reporters. Yeah, and this is a metric for the concentration of reports. Okay, now looking for characteristics over time, we plot the CVEs and the number of reporters per year. We see that they're quite closely correlated. And if we plot the average number of reports per reporter for each year, we can see no real trend. So on average, this is stable. However, we can observe something that may be interesting. For Linux, for example, a reporter makes more reports on average than for the other projects. We can talk about this later. Now about motivations, bug bounty programs, we give an estimate, a low and high estimate of the possible motivations of behind discovery. So the low estimate is the confirmed CVEs that had a bug bounty given, and the high estimate is the CVEs that were reported by a reporter that had at least 1 bug bounty in their career. And overall, we saw that bug bounties are considerable, impact considerably. But what about projects without bug bounties? Should we worry about them? Yeah, that's a good question. Now about affiliations. Here we get the affiliations from our data set. So we have internal reports. Affiliations matches the organization behind the project. Internal, then other organizations with bug bounty, then unknown affiliations with bug bounty, and then unknown affiliations. And here the interesting thing is to note that Mozilla has a lot of internal reports, but also interestingly, for Linux, we have a lot of organizations reporting, and especially big organizations. So this explains, in some sense, why the average reports per report is slightly higher. Probably it's not that Linux is more insecure. And also maybe gives an argument why we may not need bug bounties for Linux that much, because a lot of other big organizations are invested in the security. So to summarize, our contribution is a general methodology to create and analyze data sets of vulnerability reporters. It can be applied to other projects and for other research questions as well. We identified some characteristics that can act as benchmarks for healthy ecosystems. We identified this ratio, the quantitative metric for the concentration of reports. And we also looked into potential indicators of quality. So individual scrutiny metrics may be misleading, but a complete profile can be informative. And with this, I thank you very much, and I look forward to answering your questions.
Thank you very much, Nikolaos. I don't see any questions coming from YouTube or Facebook or our other channels, but I have done one for you, and it's regarding the engagement of the community in a project. So it seems that popularity and maybe the number of developers in the project is not a good predictor of the number of reporters. What is your feeling for what could be good characteristics? What factors can support engagement for reporters?
Well, I think your question may be like 2 points. So first, it's not necessary that the number of people looking for vulnerabilities is so closely correlated to how popular the project is, or to how many developers there are, which is, yes, I think that's true, because vulnerabilities are quite different than other bugs, because they don't get discovered randomly most of the time, like by users. So popularity is not necessarily a good indicator. And I think the second point was more about how to increase, like,
what other factors can use to engage reporters?
So to attract reporters, how projects can attract reporters better.
Yeah, I think Mozilla there is kind of
I mean, Mozilla is one of the pioneers of bug bounty programs, and we see it has a good effect. And just what I thought, maybe also giving out small bounties for maybe issues that are not security threatening directly, but were discovered during the search for security bugs. Something like that could also be a pretty good idea to give incentives. I mean, other incentives, of course, companies hire people that report a lot of bugs, so this is an incentive as well. Of course, there is also a very big problem with these gray markets that we have to talk about. Yeah, because they give a lot of money, like the markets that sell to governments and so on, keep them secret. So maybe we also have to discuss as a community about this. It's kind of a problem.
Bad incentives. There is a question from Alan. I just have a curiosity. How did you ensure you had unique reporters?
Yeah, I mean, the whole process, of course, is the best effort. At the end, we have these 2,000 reporters, and we go over them. And I mean, using our best judgment, we can say that they're unique. Of course, we cannot really know for sure that they're two different paired people. Yeah, of course.
Okay. Thank you so much, Nikolaos.
You're welcome.
We can now continue this session with the next and final two papers from the emerging results and vision track. The first one is going to be presented by Anna-Katharina Wickert, which is going to tell us about Python crypto misuses in the wild. So Anna-Katharina, here you go. You are now on stage.
Yeah. Yeah, thanks for the introduction. Today I will present our joint work on crypto misuses in Python. And let's start with our motivation for the work. If one looks into previous studies about crypto misuses in the wild, the results are rather alarming. They focused on Java and Android apps and revealed that 85% to nearly 100% of the applications, when they use a crypto API, misuse it at least once. The reasons are not that they developed something wrong or did a logical error. It's rather that they didn't understand the underlying primitive. So the misuse was not on a language concept, but in understanding crypto. In a controlled experiment with Python, researchers asked the developers to solve 3 crypto tasks. And there they revealed that the solutions were much more secure than these previous in the wild studies. So only every third solution was insecure. Thus we raised the questions: how are crypto misuses in other languages than in Java? And can we reproduce, or can we see the positive impact of Python libraries or crypto APIs in the wild? To answer this question, and also to support crypto analysis in multiple languages, we developed Ligma. Currently, Ligma supports the standard crypto library in Java, the JCA, and 5 different Python libraries. We started or concentrated on 6 standard misuses from literature, which you can see on the right of the screen. So they are, for example, that a developer uses insecure block mode like ECB, or doesn't add a random initialization vector for the block mode CBC. As you can see in the table for JCI, we developed support all the 6 rules, while for Python, while writing the rules, we observed that they are not possible for the 6 rules because you don't need to pass a static seed to generate a secure random. Further, some of our APIs avoid some misuses, for example, like PySalt, where we can't pass insecure block modes for IIS encryption. More details you can find on GitHub. To evaluate the misuses, we started with 895 top Python projects and analyzed 155 of them where crypto usages are in production code. Of these, Ligma identified misuses in every second project, and in total we got 1,501 misuses. But how are the results distributed, or in which projects have we found crypto misuses? In this table, you see the number of misuses for the top 10 misused GitHub projects, which include sales software like Sailor, or also libraries like Scapy. You see that only a few misuses are in the application, the light green, and much more are in the dependencies. For our overall dataset, we observed that 12 projects have misuses in their app code. After looking at the general numbers, we want to shed a light onto how the misuses are distributed among the 4 libraries we analyzed. You see that the misuses are not evenly distributed among the 5 rules. For empty crypto, for example, misuses due to an insecure block mode are most prevalent, while for cryptography, the misuse due to a constant key was the most prevalent one. We looked a bit into this in more depth. While doing so, we observed, or we think, that the good API design could be one of the reasons why some misuses are avoided. While we said that misuses, for example, for the block modes are possible in cryptography, they are only possible for part of the library, because cryptography is divided into 2 levels. One level is a high-class API design, where these misuses are avoided by design because the developer didn't need to make the choice of the block mode and can fail in doing so. While in the low-level cryptographic primitive, also called the hazmat layer, it's possible. Last, I want to shed a short light onto a comparison between our results in Python and previous study in Java and in C, which were conducted on firmware images. In general, you see that the misuses and percentage of applications with a misuse for a respective rule is lower in Python than in C and Java. We think that it's most remarkable for rule 1, which is the block mode ECB, which is the standard mode if you don't pass any further configuration for IIS in Java, while it's avoided in or while developers are supported to not misuse it in Python, like we have shown you with cryptography and PySalt. Now I want to shortly sum up my talk. I've presented you Ligma, our multi-language crypto analysis with support for JCR and 5 Python APIs. We have shown that every second app is secure, and in our comparison, we have shown that it seemed that in Python crypto misuses are less frequently than in Java and C. And we hypothesized that the API design support developers in doing so. Feel free to check out our data, our paper, and Ligma itself. Thanks for listening.
Thank you. Thank you very much, Anna-Katharina, for the nice talk. I actually have a question on the differences that you show between Python and Java. Do you think it's mostly because of how well the API are documented in the Python standard library or whatever library versus how they are documented in the Java doc, in the Java RE runtime?
Yes, I think that's also part of the reasons. So we don't have, or we don't know it for sure, but I think so. Also in Java for a long time, I think ECB was mentioned as default, and the API which is insecure, and also the landing page of cryptography nicely explained why one shouldn't use the hazmat layer. And if you look into the IIS examples, there's also always the remark, if you want to use the low-level layer, that you should be cautious when you use it. And so I think that's probably one of the reasons.
Right. So maybe bad documentation plus bad defaults.
Yeah, I think, and reasonable defaults.
And I was actually also looking at the paper, and I found something very interesting. You showed in this study that 58% of are password-related issues of the misuse cases of the API. And so, digging down in the paper, I saw that many projects use a static salt, and many use a very low number of iteration for encryption, which maybe points out to another bad default, probably. Do you have a feeling for which kind of application you have this behavior? Because it feels to me that it's kind of something related to performance. And so people, rather than storing, the salts that are generated every time, they store a single salt and reuse it, or rather than, running several iterations of the encryption, they run lower than whatever they recommended, 10,000.
That's a good one, like for the iteration count, which was most interesting for me when looking into them. It was always the iteration count of 1.
Right. Yeah.
So I think that it's kind of a copy or paste error or something, because it was like, I think 40 instances, I don't know exactly, but they all had the iteration count of 1. which was a bit
Yeah.
interesting in the sense that they didn't choose another one of 100, which would be performance related.
Right.
Yeah. And the static sort was sometimes also, I've seen once, I think, a comment that it should be changed, but you know what happens with comments in code.
Right.
Yeah.
Interesting. Okay. Since there's no more question from the chat, so we can move to the next talk. Thank you again, Anna-Katharina.
Thank you.
And let me bring up on stage the last speaker, which is going to be Luigi. And
hello, everyone.
Luigi has a paper from the Emerging Result and Vision track, web application testing using TK to detect nearly duplicate states in automated model inference. So I think this is finally a real testing paper rather than a security paper.
Yeah.
So please, Luigi, go ahead.
All right. Hello, everyone. I'm Luigi Libero Lucio Starace. I'm with the University of Naples, Federico II in Italy, where I'm a PhD student. And today I'll present some emerging results we achieved working on the detection of near duplicate states in web application model inference using a tree-kernel-based approach. As you know, end-to-end testing is a widely used technique to ensure the quality of web applications, and model-based testing is often used to support testers in this time-consuming task. For example, leveraging state-based models of the applications under test to generate test cases or test artifacts. These state-based models are typically obtained by crawling, which is to say by using tools that systematically explore the application under test. In these state-based models, each state represents an high-level feature, and transitions represent navigation relations between features. So in the example, we have a login feature from which a user can access a reset password feature or a dashboard with different commands, and so on and so forth. In practice, however, as recognized in the literature, models obtained by crawling are often affected by the so-called near duplicates. Near duplicates are states corresponding to web pages that are different, but nonetheless represent the same functionality. In the example, we have web page A and web page B, that of course are different pages. They have different text, different images, different colors, but nonetheless, they both represent the same viewbook detail functionality. This problem with near duplicates can easily get out of hand, especially when dealing with model inference of medium to large sized application. So, for example, a model obtained by crawling on our simple bookstore example could end up looking something like the one shown in this slide, with a marketplace state, and then many states, one for each of the available books, and all of these states actually represent the same viewbook detail functionality. This has an impact on the precision of the models, since we are basically adding a number of useless states, and it has an impact on the completeness of the models as well, since we are wasting a lot of time exploring all these near duplicate states, and maybe in the end we won't have enough time to explore other relevant parts of the application under test. And this, of course, has also a negative impact on the application of model-based testing techniques. The challenge is to devise effective mechanisms so that crawlers can detect near duplicate states during their exploration process and map them to a single logical page, so that the resulting models end up looking something like this. The problem of detecting near duplicate or clone web pages arises quite naturally in mainly two domains. In web indexing and information retrieval, it's a problem that search engines face, for example, to detect content plagiarism among different websites. In this domain, solutions typically focus on the content of web pages, and robust hashing techniques such as SIMHASH are typically used. While in automated phishing detection, on the other hand, techniques mostly focus on the looks of web pages rather than content, and hence techniques from computer vision are typically used. All these existing works or this solution, all these solutions detect near duplicates across different websites. And to the best of our knowledge, there is no solution specifically geared towards the detection of near duplicates within the same website and with the goal of supporting this model inference task. So in this work, we present a first approach going in this direction. Our solution leverages the tree-structured document object model representation of web pages to detect near duplicates. And in particular, we use three kernel functions, a class of kernel functions largely used in natural language processing to measure the similarity between three structured objects. And intuitively, three kernels measure similarity between two tree-structured objects by counting how many subtrees or fragments the two objects have in common. By changing the definition of what a fragment is, it is also possible to define a number of different tree kernel functions. More in detail, our approach, given two web pages that need to be classified, applies a number of tree kernel functions from the literature on them, on their tree-structured DOM representation. Each of these three kernel functions computes a similarity score in the range 0, 1. We aggregate all the similarity scores into a similarity score vector, which is then fed to a support vector machine classifier we trained using an existing dataset. As for the experimental framework we are using to assess the effectiveness of the proposed technique, we are currently replicating the procedure in a recently presented ICSI paper by Yandrapalli et al. In that work, the authors benchmark 10 near-duplicate detection techniques from different domains on this model inference task. As they do, we frame the near-duplicate detection problem as a multi-class classification problem. And we also leverage the same massive dataset consisting in about 100,000 manually annotated web page pairs to train and test our classifier. Finally, we measure performance using the F1 classification score and compare the performance of our technique directly against the performance of the 10 techniques benchmarked in the ICSI paper. Emerging results are promising and are shown in the slides. Our technique is represented by the red bar at the top, while the subsequent 10 bars represent the 10 techniques benchmarked in the ICSI paper, with visual-based techniques being depicted in green and document-based techniques in orange. Our technique achieves a 3% improvement with respect to PDIF, perceptual diff, which was the best technique among those investigated in the ICSI paper. But it's worth noting that perceptual diff is a computationally expensive visual-based technique, and this significantly limits its applicability on the model inference of large applications. Our technique is way more lightweight, and when compared against similar document-based techniques such as the Levenstein distance, we get a more noticeable improvement ranging from 10% to 30%. In future work, we plan, of course, to apply our technique on the real problem at hand, which is model inference and not a classification task. We are also working on implementing custom tree kernel functions specifically designed to detect near-duplicate web pages. And we are also investigating the feasibility of using deep learning to learn a mapping from web pages to numerical vectors, which could then be used to measure similarity between web pages in a more accurate way. So I thank you all for your attention. I'm done. And if you have any questions or feedback, I'll be really glad to hear from you. And you can also write me an email. My address is shown on the slide. Thanks again.
Thank you very much, Luigi. Very interesting work. Not myself into UI or GUI testing, but it seems a very interesting approach using tree kernel, which is usually which I've seen used in natural language processing to tackle this problem. And actually, I have a curiosity regarding how you model the web page, the DOM of the web page. So I've seen from the paper that you have three flavors to it in a way. So one with a full DOM, the second one only the body, and then a third one which kind of puzzled me with the body excluding the script tags. Can you just comment quickly why is
we preliminarily devised this way. We called it preprocessing strategies to see which parts of the document object model actually mattered. And preliminarily, we tried the three alternatives you mentioned, and in particular, the last one removes the script elements as since we use a dynamic crawler, which is Crawljax. We actually don't really care about the code that's executed in the browser, since even if there is a local code that causes changes to the DOM, it will result in a different state. So we thought that having the scripts in there could add some noise that didn't really matter to distinguish this kind of near duplicates or clone or distinct pages.
Yeah, that makes sense. And let me check the chat. Actually, I have also a final question, but connecting back to what Max mentioned in the keynote. If you, how far do you think you are into integrating this into a testing pipeline, even this preliminary results, so that you can show,
Right. So
time saving.
We actually have a working implementation of the Crawljax crawler integrating this our classification approach as a state abstraction function. So it will be possible very soon, I hope, to download our custom version of Crawljax and start inferring models using our technique. And then integrating with model-based testing frameworks will be surely the next step. And in particular, it will be very interesting to assess the impact of the model quality on, for example, the number of generated tests in a test generation approach and stuff like that.
Right. Okay. Thank you so much, Luigi.
Thank you.
Best of luck with your work. And this was also the last talk for this session. I believe this concludes this first day at ESEM 2021, and I'll see everybody tomorrow for the second day of the conference, which will start at 1 p.m. Italian time on YouTube. Thank you, everybody. Have a great day or a great morning. Bye.